Hello, everyone. We'll get started now. I'd like to welcome everyone to this iNEMI webinar to launch our call for participation for the new iNEMI project, Reliability and Loss Properties of Copper Foils for 5G Applications. If you've just joined us, I'll just remind you that your mic and webcam have been disabled, but you can use the chat function later on to ask questions at the end of the webinar. And hopefully you can all see the screen and hear me okay. I'm the project manager for iNEMI, the International Electronics Manufacturing Initiative, and project manager for this up and coming new project. And it's my pleasure and privilege to be joined today on the webinar by Ed Kelly, who's Chief Technology Officer and Senior Vice President of Technology of the Isola Group. Ed is the project leader for this project, and he's supported by two additional project leaders, John Androsakis of DuPont and Steve Etheridge of Dell. As I mentioned, this webinar will be recorded, and the recording will be available later after the sessions. So this is the agenda for today's webinar. I'll be describing, first of all, the iNEMI project development process. And as I'm expecting non-members on this webinar, I'll start by briefly introducing iNEMI, and then Ed will describe the technical background to the project and the project in detail. And I'll finish off the webinar by describing the process of how to participate in the project, both for iNEMI members and also for non-members. And as I mentioned, there'll be an opportunity for questions at the end. So what is iNEMI? For those not familiar with iNEMI, we're industry-led consortia of leading electronics manufacturers, suppliers, associations and universities. We're not-for-profit organisation, and we're funded by a membership fee. We're truly global. We have offices in North America, Europe and Asia, and members spread across the globe, which really represent the entire supply chain of electronics manufacturing. Our mission is to forecast and accelerate improvements in the electronics manufacturing industry, and we achieve this through our technology roadmap and our collaborative research projects. So the key benefit of membership is the participation in our collaborative research projects, and that gives significant benefits to our members through leveraging the resources of the whole project consortium, and of course reducing risks of technology introduction. We've over a 20-year heritage of successful projects, and it's addressed all sorts of knowledge gaps in our industry and uniquely bring together a global supply chain. We cover all sectors of the electronics industry, consumer, telecoms, medical, automotive, aerospace, and all aspects as well of the supply chain. In addition to academia and research institutes, and I mustn't forget other trade organisations who we work very closely with. iNEMI staff, such as myself, organise and facilitate the projects, and they typically last about 18 months, and they cover a wide spectrum of topics. The project objectives, they're formulated by the consortium to really ensure that the output aligns with member companies' objectives. Always there's an up-to-date list of our projects with a brief description on our website. So within iNEMI, we have a PCB and laminate technology implementation group, and that oversees initiatives and projects all concerned with printed circuit technology. Two initiatives have recently started, in addition to the project I'm going to describe today. One of these is on hybrid PCBs, and that's led by Carl Giesen of IBM. And the second on the effect of glass cloth and other criteria on CAF failure, and that's led by Juan Landros of Intel. And I'd like to stress that they're all interrelated, and you'll see today in Ed's presentation where certain types of CAF failure will come into today's project. So these topics are all interrelated and overseen under the umbrella of our PCB and laminate TIG. Now, this next slide depicts our project development process. Project ideas really come from our technology roadmap through a gap analysis that really identifies key issues that can be solved through a collaborative effort. And also our members, any members of iNEMI can propose their own project ideas. I should mention that the roadmap I've been talking about is free to members and also can be downloaded and for a reasonable fee is available to non-members through our website. So iNEMI staff, such as myself, support the drafting of a project proposal, and we arrange the meetings when an initial consortium is formed, and a detailed statement of work, or SOW, which is the actual project plan, that's defined and objectives to the project are agreed. And these are stages 2 and 3 that you can see on the chart. The SOW, that's the project plan, then goes through a stage gate process for approval by our technical committee, after which the project proper can start. And it's from stage 4 onwards that the project is limited to iNEMI members. So this slide just shows some of the key documents and the project management policy within iNEMI. A key document, as mentioned, is this statement of work, or SOW, and that sets out the purpose, scope, and objectives of the project and outlines the project tasks and the resources required, together with some sort of schedule timescale for the project. In addition, there's a project statement which is signed by the iNEMI members who wish to participate in the project, and that commits each project partner to the resources required to make the project successful. Just to summarise, so project participation does require iNEMI membership, and that's because iNEMI staff, such as myself, we administer and coordinate the project. We arrange all the webinar meetings and coordinate the various tasks to ensure the schedule's adhered to. We also support the project by publishing interim and final reports and help with the dissemination of the output of the project. I should mention, of course, that the projects are always industry-led, and the project chairs or leaders always come from our active membership. So with that, let me now introduce Ed. I'll pass you over to Ed Kelly, as I mentioned, and Ed will describe the background to the project and plans for this new project. And Ed, if you just instruct me, I'll change the slides as you wish.
Will do. Thanks, Steve. Yeah, so let's start with some very high-level drivers of the project, and I don't think any of this is a surprise to most folks on the call. But let's start with the graphic in the upper right, just showing global internet bandwidth usage, traffic by user and household per month. So if you look at 2017 to 2022, it's about a tripling of internet bandwidth usage, and obviously expected to increase from there. The graphic in the lower right showing IP traffic by application type, clearly, internet video is causing a lot of the growth in that traffic. But in addition, things like voice and data over the internet. For those of us with kids, we can attest to the fact that online gaming is also increasing, as well as the complaints about connection speeds when our kids are playing on the internet. So lots of reasons why internet traffic is going up. In addition, high-speed computing, obviously, which includes AI and blockchain technology. There's been a lot of news recently about the energy and the computing bandwidth required for things like cryptocurrency mining. And then in the automotive market, the advanced driver assist systems and the development of driverless cars, all creating demand for very high speed and high frequency equipment. So obviously that drives needs for printed circuit boards and base materials. Typically I'm oversimplifying, but the need for low decay and ever decreasing and low loss base materials Historically, that's meant much of that focus was on improving dielectric losses. So the polymers and the reinforcements that go into the base material, trying to make improvements in those. But certainly in recent years, conductor losses, especially as frequency goes up, which we'll talk about in a second, conductor losses become a much more critical consideration. Next one, Steve. So if you look at the illustration in the upper left, just as it's a simple embedded strip line, transmission line, and then the chart in the lower left shows skin depth versus frequency. So as the frequency goes up, more and more of the current travels in the outer portions of the conductor. So that means both the treatment and the roughness of the copper bonded to the laminate is important, as well as the treatment, whether it's an oxide or an oxide alternative type chemistry to improve adhesion of the outer surface of the foil to prepreg when making a multilayer. Both of those surfaces become very important. And if you just look again at that chart in the lower left, even at 10 gigahertz, you can see that skin depth is significantly below 1 micron. So a very, very low profile in terms of what our industry has used historically. And the graphics in the lower right, just showing again, as the frequency goes up, that signal's traveling along the surface, which is much, rougher. So at your actually path distance of that current or the signal is longer, leading to, higher levels of loss from point A to point B in a printed circuit board, with the solution being trying to go to ever lower levels of roughness on your copper foil. And then just some examples in the upper right of copper surfaces, from starting in the upper left of that graphic, you can see, reductions in surface roughness trying to improve conductor performance. Next one, Steve. Now there's lots of considerations here. So, again, that this particular project, the intent is to look at both surfaces, the side bonded to the laminate, as well as the side that we're bonding to prepreg when making a multi-layer printed circuit board. And also considering both signal integrity performance and reliability. If you look at the chart in the lower left, let me take a second to explain. So each of those lines is a different copper foil. From the blue line up, those are approximately 2 micron surface roughness, and then below that are 1 micron and below, with the x-axis actually representing the lowest loss or the foil with the lowest loss in this set of materials. So each of the other lines is compared to that x-axis. So the y-axis then is a percent increase in loss versus frequency for different foils. So a couple observations. One is a lot of people historically have looked in the 5 to 10 gigahertz range when comparing materials. And what I will point out is if you only do that, you may not see differences that could happen at much higher frequencies. So just that green one, for example, at 5 or 10 gigahertz, it looks very similar to the other foils in that group. But obviously, as the frequency goes up, you see a big difference. So very important to look at the higher frequency performance. The other piece, if you look at the graphic on the right, which is showing a couple of different surface treatments used in the PCB fabrication process in the photos. The sample 1 and sample 2, a couple of key points. So one, part of this project is going to look at how do we measure roughness and how does that correlate to both signal integrity, performance, and reliability, and which measures of roughness give us the best correlation. So this is showing here, if you just, the example is RA. So if RA of sample 1, RA of sample 2 are pretty much the same. But then the RSAR, which is a measure of the area measurement of the roughness. So RA is actually the same, but obviously you can see much different levels of area. And you can imagine if a signal or current's flowing along that surface, sample 2's got a much longer path to go than sample 1. So one of the things we'll be looking at is seeing if we can correlate things like those types of measurements to both signal integrity and reliability as well. Next one, Steve. So, with ultra low profile foils, the measuring systems become really important, and obviously in our industry, one of the things folks have looked at for many, many years is peel strengths. We're finding those aren't necessarily very good at predicting certainly reliability assessments, but also, and clearly signal integrity doesn't have a whole lot of correlation to that. But so one of the things we're trying to do in this project is identify, okay, how do we assess reliability when using some of these ultra low profile copper foils, and starting with, how do we measure the surface? The illustration on the left, shows examples of contact profilometry versus non-contact. You can see using contact profilometry, when you get to very low levels of roughness, you're really not getting an accurate depiction of what the roughness looks like, and really need to move to something like a non-contact profilometer to get more precise or accurate measurements of that surface. And then the graphics on the right just are examples of, on the far right, it's a picture of one of the optical measuring systems and the output next to it, showing some of the area, what the area of the foil surface looks like. Next one, Steve. So, the ultra low profile coppers obviously, create concerns about copper to dielectric adhesion, but we've seen some other failure modes as well when using very smooth copper foils. Now, in some cases, suppliers will use some sort of chemical adhesion promoter, such as silanes, to improve copper peel strengths. But these types of things can also lead to other issues, which you see here. So in the picture on the lower left, what happened was the chemical adhesion promoter on the foil actually interfered. It left a residue on the etched surface of the laminate, and then interfered with the bond between the laminate and the prepreg and bonding the multilayer together. So we actually saw delamination between the dielectrics rather than copper surface to dielectric. So that's one failure mode that we've seen. Another on the right is related to calf resistance. In this particular case, we saw some failures after, I think it was just shy of 300 hours in this particular test vehicle on a 16 mil hull wall to hull wall. The pictures on the bottom are cross sections. So you can see in the red boxes, that's the bond line between the etched laminate surface and the prepreg interface. And while we didn't see delamination here in calf testing, we did actually see copper migration at that interface. We've repeated that enough to convince ourselves that it was related to the adhesion promotion on that particular type of copper foil. So a couple of different failure modes besides traditional delamination between copper to dielectric that come up when we're looking at these copper foils. Next one, Steve. So with all that in mind, our project, is looking to achieve a few things. We're looking to start with, creating some common ground, if you will, in specifying surface topography. And that includes both the copper foil, which IPC committee is working on, and I think preparing to publish, non-contact methods and establish grades of roughness, but also to see if that surface profilometry can be used to assess the other side of the copper foil, where an oxide alternative or other type of surface treatments used to promote adhesion between that surface and the prepreg, making the multilayer. And then really, trying to see if we can, use that profilometry and identify characteristics of the copper and the bonding treatments, and correlate those to both PCB electrical performance as well as reliability in a multilayer. So we're hoping that output there then can help reduce, product qualification costs with that data established. and if nothing else, at least establish a good procedure for people to use when evaluating ultra-low profile coppers with ultra-low loss dielectrics. That's the other piece we haven't really talked about. But the other, when using these ultra-low profile coppers, typically they're going to be bonded onto, a very, extremely low loss dielectric material. And often those just inherently don't have as much adhesion to copper as some other materials like epoxies. So, the low profile copper and, dielectrics or polymers that, are a little bit more difficult to bond to copper, create both of those challenges. Okay, next one, Steve. Okay, moving, into the project here. So, we foresee, once we have our group established, we'll want to get everybody on the same page. So we'll have some, benchmark of current and basically existing work related to this topic, and then focus on, basically agreeing on our profilometry methodology, and assuming that's non-contact, looking at various copper types, copper thicknesses, different chemical treatments used for the other side of the surface. Now, the IPC specification is related to the surface bonded to the laminate. We intend to see if, we can generate enough data on the surface treated side to maybe provide data to standards bodies to see if that type of methodology and characterization can be useful for standards organizations as well. And then, once we'll talk about it in a second here, but we'll design some experimentation to look at, the characteristics of roughness out of the non-contact profilometry, see if we can correlate those parameters to signal loss at high frequencies, as well as reliability considerations. So, we don't know if it's going to be practical, but it would be nice if we could use these types of profilometry methods as a process control tool, for example, making sure as we're building printed circuit boards, we can predict whether we get the signal integrity and reliability that's required. Next one, Steve. Okay, so I promise not to read everything on this chart, but I will, take the opportunity to describe both what, kind of summarize what the project is. But let me first start with what we are not going to undertake in this project that often doesn't get talked about. So we're not looking to develop new standards. However, we think some of the data we collect here might be useful to, the standards development bodies like IPC. We're not intending to develop or define pass-fail criteria. There's just simply too many variables and, many applications with different requirements in order for us to do that. We don't intend to develop new methodologies for measurements. For example, profilometry systems. We intend to use what's available today, focusing on the non-contact methods. And then we're not going to make assessments of particular metrology systems or the suppliers of those systems, or promote specific suppliers of copper, the oxide alternative chemistries, or laminate material types. As far as what the project is, so I think you've gotten a pretty good idea, but starting with, understanding the existing work that's out there, and then aligning on terminology for topography. So that's, adopting basically the IPC specifications for surface roughness and using non-contact methods to measure it on the side bonded to the laminate. We'll see if that can also be used on the other side that's surface treated with an oxide alternative or other type of chemistry. And then look at the different types of outputs, different measurements of roughness to see what best correlates to both reliability and signal integrity. And then for the, if you drop down to that fourth line there, much of the early phase, which we'll talk about in a second, is going to be looking at setting up testing to look at different types of copper foils with different levels of roughness. Use those non-contact methods to assess signal integrity. So that's focusing primarily on the foil to copper-clad laminate surface. We'll try to use both simulation and experimental methods to measure and assess the signal integrity performance. And then likewise, to characterize the surfaces on the external bonding side. So again, trying to correlate roughness parameters on the surface treated side, again, to both signal integrity as well as reliability. Part of this is also going to be a discussion about, so if peel strength is not a great measurement of reliability for these types of foils and laminate materials, what might be, and can we correlate those surface roughness to reliability, or do we need some other types of test methods to look at the laminate materials and in process and PCB manufacturing, looking at the surface treatment to see if we can predict reliability before we're actually building a printed circuit board. All right, next one, Steve. So this is just a target project schedule. Overall, the expectation is that we would try to achieve a series of tasks over 18 months. With any good project, it usually suggests additional work that you do in the future. So we're thinking that there's probably a phase 2 that comes after. But then when you break down the task 1, 2, 3, and 4, which we'll talk about in a second, we'll try to do as much of those tasks in parallel as possible. Next one, Steve. Okay, so for task 1, again, the title is DOE, or design of experiment, but really to begin, we want to get the entire group grounded with some common knowledge and understanding of the state of the art. So reviewing what data is available in the industry, what's publicly available, reviewing some of the profilometry methods, those non-contact methods as defined by the IPC test method you see here, 2.2.22. And then kind of designing that. I expect this to require significant amounts of discussion because as everybody knows, there's many variables that can affect these things. So we want to make sure we're defining the scope sufficiently so that we can be successful in setting up a manageable design of experiment with good results at the end. But it would include a range of types of copper foil, range of thicknesses of copper foil, as well as both sides, the side bonded to the laminate and the surface treated side. We'll also agree on which dielectric materials to use in this study to make sure that we're selecting materials that people would actually consider using in these types of applications. And then, again, probably requiring a lot of discussion about what the test vehicles look like. And that includes both for signal integrity performance as well as the measures of reliability. So how do we assess the reliability in addition to the signal integrity? There will be, we'll discuss, how we might model the insertion loss in advance, and then how and who's going to support the actual measuring up to what frequency. What did I miss there? Anything? Oh, the range of oxide alternative or surface treatment chemistries to consider as well. Okay, task 2. Once we have that designed, it's all about execution, right? So study 2, will correlate between the copper topology and signal loss. Again, that's using the modeling to predict what we'd expect, as well as fabricating the test vehicles, which includes the different types of laminate, copper foil, and bonding treatments, and then perform the actual measurements. Task 3, similar types of work, but then focused on the reliability. So that's both adhesion between the ultra low profile coppers and the dielectrics, but also making sure we're looking at those other failure modes shown earlier, where you can see delamination between the dielectric interface in laminate and prepreg, or potentially CAF along that bond line as well. And I think, yeah, so and then task 3 also encompasses, again, we're searching for some way to predict reliability without having to build and test an actual multi-layer PCB. So something that might substitute for copper peel strength. Certainly we'll look at copper peel strength, but we expect that we'll need some additional types of test methods in order to predict reliability. And see, one of the things we'll look at is whether those surface roughness parameters can be used to predict reliability as well. Next one, Steve. So really, to kind of summarize all that, what we see as the benefits and the value to the industry, I think in short, there are some other projects going on that are focused on things like copper peel strength or focused on strictly signal integrity measurements. We do expect this project to be complementary to that in looking at both sides of the copper foil, so the treated side, with looking at roughness, but also looking at the surface treated side with oxide alternatives, to look at both sides of those copper foils and not just focus on signal integrity performance, but as well on reliability. We think that may be a benefit to the industry and to users having that data. We hope that folks can avoid, can predict what they need in terms of materials to achieve both signal integrity and reliability without over specifying on the materials and paying a higher cost. So those are some of the benefits that we believe the project can offer. And again, I mentioned this earlier, but I think given the range of applications and designs out there, we think the approach that we develop in this project may be useful, across different design spaces. So the same approach might be able to be used relatively quickly. So establishing a procedure about how do you evaluate and qualify these types of materials in your applications may also be a benefit to the industry. And I think I'll leave it there. Steve, anything to add?
Thank you, Ed. No, thanks. That's excellent. Thank you for setting the scene on this new project. And now, for the next few slides, to finish off, I'm just going to describe how to participate with this project. We've held a number of pre-project meetings already with a core of potential project team, and that has helped produce the project plan, which Ed has just described, and the statement of work. So we've had there are two calls for participation webinar. This is session 1 that you've all joined, and I think in about 8 hours time there's session 2, which will be hopefully in the morning in Asia to allow colleagues there to join it. But of course we may have others in other regions as well join it. Now this when the session 2 finishes, that signifies the start of what we call the sign-up process, which is a little flexible, but I put down there approximately 6 weeks, and we'll be looking, that will effectively be all of June, and we'll be looking to start the project very early in July. And there is a deadline there, but we appreciate there's challenges of signing off on a research source commitment, so there's a little bit of latitude there for signing up. We will hold regular project calls by Microsoft Teams, such as today, and of course with the project meetings everybody will be able to use their webcam and microphone, be assured of that. And as usually meetings are every 2 weeks, and the duration, as Ed has described, is usually about 18 months or so. So this I've got 2 slides coming up. This one is for iNEMI members. For non-members, if you be patient, the next slide will be for them. So for existing iNEMI members, it's a very simple process. And you really download the project statement, the PS, which can be downloaded from our website very shortly, or you can email me and I'll send you the SOW and project statement. They're in the public domain, so they're available for anybody to download, but I can email them to you as well. And then you just need to print off, sign, scan, return by email the project statement. It needs a signature of the participant and probably of management approval for you. And then my colleague Grace O'Malley, the iNEMI Vice President of Technical and Project Operations, will countersign it and approve your participation and send you back that completed project statement document. So very simple process for iNEMI members, but any questions I'll be happy to answer. Okay, for non-members, then, as I mentioned, when we start the project, at the moment, all the meetings and the meetings in the coming month, I should add, the meeting's already scheduled over the next 4 to 6 weeks. They'll be open for all industry. They won't be restricted to iNEMI membership. But when the project formally starts, then it will be restricted to those that have signed up for the project. And so that really means considering iNEMI membership. And we can help with that by arranging one-to-one calls with you to present iNEMI and all the benefits of it and the mechanism of joining. So I do recommend that you contact me or any iNEMI staff member. If you look at the website, there are staff members in different regions. You may want to contact one nearer you geographically. I'm based in the UK, but everybody can contact me if they wish. There's already information on the website about membership. That's the fees, the sort of legal documents where it covers IP and other issues. And there's also an application form there. And as I said, you can download and review the statement of work. But I can send you all these. If there's any problem with downloading it, just contact me and I can arrange that. And so lastly, any questions? So as we've had quite a lot of people join us with this Teams meeting, as I said, I was sort of obliged to arrange it so that the mics were disabled. Otherwise, from past experience, there's so much background noise. So I apologise in advance for that. But the chat function should be available to you, and I'll keep an eye on that right now for a few more minutes. But you can always contact me if you've got questions for Ed Kelly. You may know his contact details already, but by all means, email me and I'll pass on. Ed and I will answer the questions on the project itself, and I can help with answering any questions on joining the project, participating with it in the future. So I'd like to finish by thanking everybody for joining us on this webinar. And I'll just put myself on mute for a few minutes to see if there's any questions coming by chat, and we'll try and answer it either right now or by email. Thank you very much, everybody. And thank you, Ed.
Yeah, thank you. Steve, I do see, I think there's a couple of questions in the chat. I see some from Art Morris. Will the project address simulation methods and model properties in commercial E&M tools to properly predict loss over frequency, including the roughness characteristic geometry? So in short, we do intend to do some simulation and modeling. However, the focus isn't so much on evaluating those tools for this particular project. But we do want to try to simulate and predict as we begin building the test vehicles. Other question was at higher frequencies, we're also typically using smaller line and space and package pitches with metal defined pads. How do these trends affect the reliability trade-offs for the low loss foils? So I guess a short answer would be, that implies on the PCB, tighter pitches or distances between features, whether it's hole to hole, to conductor, line to line, things like that. So certainly that has an impact on, the complexity of the board can impact, the lamination resistance of a combination of copper and dielectric. So And then also, as those features get, the distance gets smaller and smaller between features, that concern over the calf resistance becomes a little bit more significant. So I think, my expectation is that we would capture some of those things in the design of the test vehicles we use in the project, which we haven't done those designs yet. That'll be part of the project. And then the last question I see is, what about the loss and reliability impacts from surface treatments such as masks or other coatings? So I assume surface finishes. So this particular project, we're not intending to investigate those particular items, although we certainly recognize they have an impact as well.
Yes, good point on the last point. Then, Ed, I think as you may have seen on the timescale slide, there was a phase 2, and I think the surface finishes of the copper tracks, together with solder masks, maybe conformal coating, that type of treatments or coatings, may be part of the phase 2. I think that we've briefly discussed that already, and that will be better defined as phase 1, the project that you've seen, progresses.
Yep, good point.
And just to remind people, as I mentioned right at the beginning, Ed mentioned CAF as well, and particularly with his bond line, with reducing pitches and distances between via holes and other copper features. Then we have got a follow-on project on CAF that will be, I'm sure, will be complementary and supplementary to this project, but specifically looking at CAF failures. So that's important. And of course, as when you join iNEMI, join this project, then you'll have access, the ability to join both projects as well, the CAF project as well. Okay, Ed, can you see, is there any more?
I don't see any other questions in the chat.
Okay, I'll give it another minute or two, and then we'll, if we don't have any more questions in the chat, then I'll close the meeting in 2 minutes' time. So again, thank you very much for your participation. And as I've left my email address there, I hope you made, you should have the contact from the previous emails that sent out, but please make note of it, and you can follow up with myself anytime you wish.
Steve, one question here. Are we going to share the presentation via email or iNEMI download?
Yes, good question. This session is recorded, and the second session too will be recorded. The recordings will be available, and the presentation should be available, and it can be sent out. But if you specifically want it in the very short term, then do email me, and I can probably get you certainly a copy of the presentation in advance of it being on the website. It can take a few days for the recording and presentation to appear on the website, so don't hesitate, but they will be available. Yes.
One more, Steve, on the projected start date. And I think
projected start date will be very likely early in July. I'm going to say first, probably the second week in July, probably first or second week in July, to start the project. So that's what we're aiming for. Now, if you're still in the process of joining the project and just going through the paperwork, then that there was some latitude there, then you're welcome to join in as we start the project. We realise that as long as we've got your intention to join and it's going through the process of the paperwork, then that's fine. But we're looking to start very early in July.
One more question. Is there already a one max frequency, or is it as high as measurement equipment can go today?
Good question.
Good question. Yeah. So I think there'll be some discussion on that. I think, at a minimum, we've had some discussion. I think we're probably talking at least 50, 60 gigahertz, depending on who's got what measurement equipment. Maybe we'll go higher than that, but that'll be part of the project planning.
Yes, that raises another point that Ed's described the project in some detail now, but if you join, those that join the project will still have an opportunity to influence some of the details of the task and objectives. They're fairly broad, as Ed described. So, that is still an opportunity for you when you join to have some influence over the details, if you like, of the individual tasks and some of the objectives. Just waiting another minute or two, as we've just had some late questions there. I don't want to cut anybody off that has some more questions to answer. Okay, I think I'll be closing the webinar in about a minute's time, unless somebody's busy typing away for another question. Hopefully we've answered them all now, and so I'll close the webinar in a minute's time. Thank you everybody for joining. Thank you.